Hello, in this lecture I will explain what is mathematical induction. A mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. We have two stages in a mathematical induction. In the first stage, we will check if the statement is true for n that equals to 1, and only after we pass the test and it is indeed true for n that equals to 1, we will proceed to the second stage, and in the second stage we will assume that the statement is true for n, and when we rely on this assumption we will prove that the statement is also true for n plus 1. So in the second stage we will create two equations. The first equation will be the expression of the statement for n, and that will be also the induction's hypothesis or the induction's assumption. So we assume that the statement for n is true, and we will rely on that assumption in order to prove that the statement for n plus 1 is also true. So we will also create the second equation that will be the expression for n plus 1 of the statement, and we will prove that the statement for n plus 1 is true by relying on our assumption that the statement for n is true. Okay, so that will be the two equations that we will create, and after we proved that the equation for n plus 1 is also true, actually we proved that the statement is true for all the natural numbers. Okay, so now I will explain what is the logic behind the mathematical induction's proof. You should remember that in the first stage we check if the equation for n plus 1 is true, and we found out that the equation that for n that equals to 1 is indeed true. And in the second stage we deduce that if the expression for n is true, the expression for n plus 1 of the statement is also true. So we can say that now that we know that the statement is true for n that equals to 1, we can also say that the statement is also true for 1 plus 1, that is 2. According to our general proof that if it is true for n, it also must be true for n plus 1. Okay, And now that we know that the statement is true for n that equals to 2, we can again repeat on the same process, and we can say that the statement is also true for 2 plus 1, that is 3, because of the fact that we proved in general that if the statement is true for n, it must also be true for n plus 1. And now that n equals to 2, we can say that the statement must be true for 2 plus 1 also, that is 3. And we will repeat on the same process in order to prove that it also true for n that equals to 4, because now that we know that the statement is true for n that equals to 2, it also must be true for 3. Now that we know that the statement is true for n that equals to 3, we can deduce that the statement is also must be true for 3 plus 1, that is 4, according to our general proof that if it is true for n, it also must be true for n plus 1. And now n equals to 3, so it must be true also for 3 plus 1, that is 4. So we will repeat also in the same process in order to prove that the statement is true for 5, 6, 7, etc. So in this way, we actually proved that the statement is true for all the natural numbers. Okay, so in order to clarify the issue, I will give you 2 examples. We will start with the first example, that is 1 plus 2 plus 3 plus n equals to n times n plus 1, all divided by 2. So we have to prove that this statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. We have to prove that this statement is true for all the natural numbers. Okay, so we will start with the first stage. That is to say, we will check if the statement is true for n that equals to 1. Okay. So in this side of the equation we will have 1 only, because n equals to 1. In the other side of the equation we have n times n plus 1, all divided by 2, so n equals to 1, so it is 1 times 1 plus 1, all divided by 2. And this is equals to 1 times 1 plus 1 is 2, divided by 2, equals to 1 times 2 is 2, divided by 2, 2 divided by 2 is 1. Okay, so here we actually verified that the statement is true for n that equals to 1. In this side of the equation we have 1, and the other side it is n times n plus 1 divided by 2, so it is 1 times 1 plus 1 divided by 2, and 1 times 1 plus 1 is 2, so it is 1 times 2 divided by 2. 1 times 2 is 2, and 2 divided by 2 is 1. So here we can say that we indeed found out that the statement is true for n that equals to 1. Because we have here identity. The two sides of the equation are equal to each other. So we can deduce that the statement is true for n that equals to 1. Only now we can proceed to the second stage, and in the second stage we actually will assume that the statement is true for n, and when we rely on this assumption we will prove that the statement is also true for n plus 1. Okay, so first of all we will create the first expression or equation for n, and the expression for n will be 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this equation will be the induction's hypothesis, or induction's assumption. We assume that this statement for n is true. That is the induction's hypothesis. 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. Okay, so that is the induction's hypothesis, and when we rely on this assumption that this equation is true, we will prove that the expression for n plus 1 is also true. So we will create now the expression for n plus 1. It actually will be 1 plus 2 plus 3 plus n plus 1, because it is the expression for n plus 1, so we will add the numbers until we arrive to n plus 1, and it includes also n plus 1. So this is the expression from this side of the equation. In the other side, in the original statement, we have n times n plus 1 divided by 2, but we want to create the expression for n plus 1, so and this is the expression for n, so whenever it is written n in the original statement for n, we will write n plus 1 because we want to create the expression for n plus 1. So here instead of n it will be n plus 1, and also here instead of n it will be n plus 1, so it will be n plus 1 plus 1. Okay, so we write down the expression for n plus 1, and instead of n we will write n plus 1, so it will be n plus 1, we open the brackets, and instead of n we will write n plus 1. So it is in the original expression n plus 1, so we have the expression for n plus 1, so instead of n we will write n plus 1, and in the original expression it is n plus 1, so it will be n plus 1 plus 1. Okay, and all divided by 2. So as you can see here in the second equation, instead of n we wrote n plus 1. Here it is n, so we write n plus 1, and here it is also n, so we write n plus 1. Here we add 1, here we also will add 1. Okay, so it is actually n plus 1 times n plus 1 plus 1, and n plus 1 plus 1 is n plus 2, so we will write it down. So it actually will be n plus 2 plus 3 plus n plus n plus 1 equals to n plus 1 times n plus 1 plus 1 is n plus 2, so we write n plus 2, all divided by 2. So the expression that we have to prove for n plus 1 will be 1 plus 2 plus 3 plus n plus 1 equals to n plus 1 times n plus 2, because n plus 1 plus 1 is n plus 2, all divided by 2. So in order to prove that the second equation is true, we should watch on this expression 1 plus 2 plus 3 plus n. Actually it is identical to this expression, is exactly the same, and this expression in the green color equals to n times n plus 1 divided by 2, and this expression equals to this expression, so we can say that this expression equals to this expression. Okay, so we can substitute this expression by n times n plus 1 divided by 2. We can substitute between them because they are equal to each other. Okay, so now we will create, we will write again the second equation that we must prove, and we substitute this expression by n times n plus 1 divided by 2. So it will be, the second expression that we have to prove will be n times n plus 1 divided by 2. Instead of 1 plus 2 plus 3 plus n, we will write n times n plus 1 divided by 2. We can write it because they are equal to each other, and the rest of the equation will be exactly the same. So we'll copy the rest of the equation of the equation 2. So it is n times n plus 1 divided by 2 plus n plus 1. So we write here plus n plus 1 equals to n plus 1 times n plus 2 divided by 2. So we will write it n plus 1 times n plus 2 all divided by 2. So this is the expression for n plus 1 that we have to prove. In order to prove that this expression is true, we will divide both sides of the equation by n plus 1, because we have in both sides n plus 1. So we'll divide the equation by n plus 1. We'll get that n times n plus 1 divided by n plus 1 is n, all divided by 2, plus n plus 1 divided by n plus 1 is 1, equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and it is divided by 2. So after we divide both sides of the equation by n plus 1, we get that n times n plus 1 divided by n plus 1 is n divided by 2 plus n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 will be n plus 2 divided by 2. So here we can separate this expression to two parts, and it will be actually n divided by 2 plus 2 divided by 2. So we'll write it down. So when it is n divided by 2 plus 1, we copy this expression here, and it equals to, after we divide this expression to two parts, we got that n plus 2 divided by 2 equals to n plus 2 plus 2 divided by 2, and 2 divided by 2 is 1, so we will write it down. So we got here identity, n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we proved that the second equation for n plus 1 is true. Or in general we proved that if the statement for n is true, if the statement is true, the statement for n plus 1 is also true. And in this way we actually proved that this statement is true for all the natural numbers, and about the logic behind it, I explained it to you previously, so I will not repeat it, but we proved that this statement is true for all the natural numbers. 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. This statement is true for all the natural numbers. Okay, so now I will give you the second example. The second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared all divided by 4. So we have to prove that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared all divided by 4. So we have to prove that this statement is true for all the natural numbers. So in order to prove it, we'll start with the first stage. That is to say, we will check if this statement is true for n that equals to 1. Okay, so in this side of the equation we will have 1 to the power of 3 because n equals to 1 equals to n squared times n plus 1 squared divided by 4. N equals to 1, so it is 1 squared times 1 plus 1 square all divided by 4. Okay, and 1 square is 1 and 1 plus 1 is 2, so it is 2 square divided by 4. 1 times 2 square is 4 divided by 4. 1 times 4 is 4 and 4 divided by 4 is 1, so 1 to the power of 3 is 1. 1 equals to 1, so we have here an identity. So we checked that this statement is true for n that equals to 1. In this side of the equation we have 1 to the power of 3 that equals to 1, and in the other side of the equation it is n squared times n plus 1 squared divided by 4, and n equals to 1, so it is 1 squared times 1 plus 1 squared divided by 4, and 2 square is 4, so it is 1 times 4 divided by 4. 1 times 4 is 4, and 4 divided by 4 is 1, so 1 to the power of 3 is 1. 1 equals to 1. So we verified that this statement is true for n that equals to 1. So we passed the test, and now we can proceed to the second stage. Okay. That is to say, we will assume that this expression is true for n, and when we rely on this assumption, we will prove that the expression of this statement for n plus 1 is also true. So actually we will create two equations. The first equation will be the expression of this statement for n, and we will assume that this expression for n is true, and this will be actually the inductions hypothesis. Or induction assumption. We assume that this statement is true for n, so it will be 1 to the power of 3. The expression for n will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 2. Okay, so this is the expression for n. Actually it is the same exactly like the original statement. Okay, and this is also called the induction hypothesis or induction assumption. We assume that this equation is true. This equation for n is true, and when we rely on this assumption, we will prove that the expression of the statement for n plus 1 is also true. So now we will create the expression of the statement for n plus 1. It will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared. Actually now we create the expression of the statement for n plus 1, so it will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals, so here, as you can see, we want to create the expression for n plus 1, the expression of the statement for n plus 1. So we will add numbers until n plus 1. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, because this expression is for n plus 1. So we will add numbers until n plus 1 to the power of 3 include n plus 1 to the power of 3. So this will be this side of the equation for the expression for n plus 1, and in the other side of the expression we have in the original expression that is for n squared times n plus 1 squared all divided by 4. Another mistake. It is divided by 4, so this is actually the expression for n, and we want to create the expression for n plus 1. So wherever it is written n in the original expression, we will write n plus 1 because we want to create the expression for n plus 1. So instead we substitute n by n plus 1, and then instead of n squared we will write n plus 1 squared, and instead n plus 1 we will write n plus 1 plus 1. Okay, so we write it down now. So it will be equal to n plus 1 squared times n plus 1 plus 1 squared all divided by 4. So as I've already told you, instead of n we will write n plus 1 because this expression is for n plus 1, so n squared will become n plus 1 square, and n plus 1 will be n plus 1 plus 1, because it is for n plus 1 when we substitute n by n plus 1. Okay, so here we have n plus 1 plus 1, and n plus 1 plus 1 equals to n plus 2, so we'll write it down. So the expression for n plus 1 will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square, because n plus 1 plus 1 equals to n plus 2 square, all divided by 4. Okay? So what I told you, instead of n plus 1 plus 1, we wrote n plus 2, and the rest of the equation is the same. So we actually have to prove that the second expression is true. This expression is true. When we rely on this assumption that this equation is true, and this is the induction hypothesis. So if we look on this expression, the expression for n, it is actually this expression equals to this expression. It is identical to this expression. And this expression equals to n squared times n plus 1 squared divided by 4. So, and this equals to this, so we can substitute this expression by n squared times n plus 1 squared divided by 4, because they are equal to each other, so we can substitute between them. So we'll do it now. One to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus we actually, as I already told you, so that this expression equals to n squared times n plus 1 squared divided by 4. So we can substitute this expression by n squared times n plus 1 squared divided by 4. So we'll do it now. So instead of 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, we will write n squared times n plus 1 squared divided by 4. I've already told you that this expression equals to this expression, so we can substitute between them, and we will copy the rest of the equation as it is. Okay, plus n plus 1 to the power of 3, we'll copy it here, equals to n plus 1 times n plus 1 squared times n plus 2 squared. divided by 4. So we'll copy it as it is. Okay. So the only thing that we did here actually is to substitute this expression by the identical expression, that is n squared times n plus 1 squared divided by 4. And we copied the other part of the equation as it is. Here it is n plus 1 to the power of 3, we copied it here, and equals to n plus 1 squared times n plus 2 squared divided by 4, so we copied it here, and we actually have to prove that this equation, that is the statement, that is the expression of the statement for n plus 1, is true. So in order to prove that this expression is true, we will divide both sides of the equation by n plus 1 squared. Okay. You have n squared times n plus 1 squared divided by n plus 1 squared is n squared, and we divide it by 4, plus n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, equals to n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared, and we divide it by 4. Okay, so after we divided both sides of the equation by n plus 1 squared, we got that n squared times n plus 1 squared divided by n plus 1 squared will be n squared, and we divide it by 4, and n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared, and we divide it by 4. Here we can multiply both sides of the equation by 4, so we do it now, and we will get that n squared plus 4 n plus 1 equals to n plus 2 squared divided by 4. So after we multiplied both sides of the equation by 4, we got that n squared divided by 4 times 4 equals to n squared, and n plus 1 multiplied by 4 will be 4n plus 1, and n plus 2 squared divided by 4 times 4 will be n plus 2 squared. Okay, so here we'll open the brackets in both sides of the equation. So after we open the brackets, we got that n squared, and 4 times n is 4n, 4 times 1 is 4, 4 times 4 is 4, and in the other side of the equation is n plus 2 squared. It is like n plus a plus b, that equals to a squared plus 2ab plus b squared, so n plus 2 squared equals to n squared plus 4n plus 4. So we actually got here identity, and we can say that the second expression for n plus 1 is true. The second expression of the statement for the expression is true. Or we can say in general that if this statement is true for n, then it must be true also for n plus 1. Okay? And by checking that this expression is true for n that equals to 1, and then by proving that if this statement is true for n, then it also must be true for n plus 1, we actually proved that this statement is true for all the natural numbers. And I explained to you previously why we can deduce that it is true for all the natural numbers, so I will not repeat on the same explanation, but we can summarize the lecture on the mathematical induction, and we can say that mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer, like 1, 2, 3, 4, 5, 6, 7, etc. And we have two stages in mathematical induction. In the first stage, we will check that the expression or the statement is true for n that equals to 1, and only if we passed this state and it is indeed true for n that equals to 1, we will proceed to the second stage. And in the second stage, we will assume that the statement is true for n, and when we rely on this assumption, we will prove that the statement is true for n plus 1. So we will create two equations. The first equation is for n, that is the induction's hypothesis or induction's assumption, and the second equation will be the expression of the statement for n plus 1, and we will prove that the second equation is true when we rely on our assumption that the first equation is true. Okay, so in this way we actually proved that the statement is true for all the natural numbers, because in the first stage we verified that the statement is true for n that equals to 1, and in the second stage we proved that if the statement is true for n, it also must be true for n plus 1. So we can say that because of the fact that the statement is true for n that equals to 1, we can deduce from the second stage that it also must be true for 1 plus 1. Because we proved in general that if it is true for n, it also must be true for n plus 1. So it must be true for 1 plus 1 that equals to 2. And when we know that it is true for 2, we will repeat on the same process in order to prove that it is also true for 2 plus 1 that is 3. And so on. After we prove that it is true for n that equals to 3, we will repeat on the same process in order to prove that it is true for 3 plus 1. And we can deduce that it is true for 3 plus 1 because we proved in general that if it is true for n, it also must be true for n plus 1, and n equals to 3, so if it is true for 3, it also must be true for 3 plus 1, that is 4, and so on and so on. In this way, we will prove that the statement is true for all the natural numbers. So actually, this is the logic behind the mathematical inductions proof. Okay, thank you very much.